You measure through polarization, cross-correlation between polarization and temperature in the CMB, for example. And well, these you can measure from temperature three-point functions. Okay, now the thing is how many more triangles you get as you get more data, right? And the reason why one likes this type of correlation between long modes and short modes is that you can keep correlating long scales that you understand very well with smaller and smaller scales. While if you want to put a better bound on this, you need smaller and smaller equilateral triangles. And at some point, the CMB, even though it's a very good two-dimensional picture, starts getting a little bit fuzzy, and which is related to the damping of the. So if you look at the CMB temperature, two-point function delta T is a function of L. At some point, you need to start competing with a decaying exponential. And so if you want to get smaller and smaller equilateral triangles, you're going to have to compete with this. Well, if you can at least keep some long baseline, then okay, you still need to beat this, but at least you have some long modes that you control well and you cross-correlate
You're
those.
getting one smaller power of AS and some work.
Yeah, so the scale. That's right. So the scaling with L max that you're allowed to probe goes better. It goes more like the area of the screen here. It goes like L max squared, while here it grows linearly, the signal to noise squared. So here's like square root of L max, well here is linear in L max, something like that.
And the other configuration that we were talking about, so where the short mode is actually between the polarization.
You wanted this, right? This 1, 2, 3, and you wanted graviton here, and the scalar, and some messenger here, right?
Well, or for that matter, it could be a scalar, right?
Right. Yeah. I think this should go. Yeah, if you stick in here massless scalar, probably you should do as well as the local non-Gaussian in terms of mode counting. But I haven't done this. I studied more the scaling, the fundamental noise level for these types
just
of.
In terms of the principle, again, it's still going to be a polarization now 3-point function.
Yes. No, there's a temp. It's always, for example, BTT, polarization, temperature. Yeah. So the B mode polarization of the CMB photons is sensitive to gravitational waves.
But you don't get the advantage over the equilateral in this configuration that you would get in the pure scalar case?
I haven't studied this example, so I can't. Naively, I would say yes, but I haven't studied this example, so I'm not sure. I mostly studied examples with scalars for this. It's like Fisher analysis, very naive, but it sort of works for the error bars we have at the moment. Okay, yeah.
With no further ado, happy to set the second.
Okay, so every good lecture should start with a recap of last lecture. So let me do that quickly. It sets the stage for the new people in the audience. So we discussed primordial perturbations that are the initial conditions from which our universe evolves. You need the slightly bumpy initial value surface for our universe. And we have, to explain the data, all we really need is a Gaussian scalar field, this curvature perturbation. And it has a typical size of 10 to the minus 5, almost scale invariant, with some detected scale dependence of order 10 to the minus 2. And within the umbrella of slow roll inflation, we know that it's controlled by the ratio of these two scales, the Hubble scale during inflation and the typical scale of motion of this background, the kinetic motion of this background scalar field. And of course we have the graviton that I tried to argue based on these simple parametrics here of the size of the scalar the tilt of the scalar perturbations and the tensor to scalar ratio, that perhaps they could be somehow comparable, because we have detected this and this we haven't, so maybe we are around the corner. And of course you can model build your way out of this and push R to be very much undetectable, but who knows? Within this simple umbrella of models of slow roll inflation, it's plausible that we are close to a detection, in which case then this is huge. So detection would really mean that we could do particle physics at insanely high energy scales. You're like 5-6 orders of magnitude away from the Planck scale here. So you could even dream, how can we detect like some signature string theory or something like that from the statistics of these primordial perturbations. Okay. So to probe this particle physics, one way to do that is to go to these non-Gaussianities, probe interactions. Mostly I focused on 3-point functions, so I just want to when you look at an equilateral triangle in the sky, if you look at this surface and you try to correlate 3 modes of approximately same momenta, then they were sourced at the same time during inflation, because then they get redshifted by the same amount. Therefore, you're probing just a self-interaction. Okay? If you try to create a hierarchy between these modes, if you try to squeeze the triangle, then the signal is going to decay. Essentially, because one way to think about it is that interactions come with derivatives, and then this is kind of counting. You need at least 2 derivatives to be consistent with this being a Goldstone boson. So this will decay as K1 over K2 squared as I take K1 much less than K2 order K3. So the decay rate of this correlator in this what we call squeeze limits, when you take K1 to be much smaller than K2 or K3, tells you something about the spectrum of the theory, what sorts of particles are active during inflation. And because this is an experiment that the universe runs for us at 10 to the 13 GeV, potentially, then anything that is light in these units will be active and can mediate an interaction. And then the question is, how do we do particle spectroscopy with this? How do we measure particle properties? So this is, for who just arrived, this is the 1.5 hour summary of the last 1.5 hours. Let me carry on. Yeah.
Could you clarify for the massive graviton why there's 4 degrees of freedom when the conformal dimension is 2 or 1?
Because if you write the Fierce-Pauli, if you write the Fierce-Pauli term for the massive, it takes some d mu hij squared minus m squared. Now I don't remember something like. I don't remember. So you write some.
2h squared. Or you want the.
Yeah, no, I just wanted to write the Fierce-Pauli term.
Squared minus h squared.
Yeah, it's h mu nu squared minus h mu mu squared, right?
Yeah.
Then what happens that if you Stuckelberg this and if you take h mu nu to h mu nu plus sort of d, I'm gonna mess this up, but something like d mu d nu, maybe there's something, maybe Rachel can help me, maybe there's a term that goes like g mu nu here.
Yeah, there's a conformal factor and it multiplies h squared, big H squared.
Right, for units you need h squared here. There's some scalar mode that decouples when you tune the mass, when you set m squared. Just like if you take the Fierce-Pauli action, and when you set the mass to 0, there's a vector decouples, right? And you get GIF invariance here. There's something that's called partial gauge symmetry that removes the scalar mode. So you end up with 4 degrees of freedom. But this is just, okay. Maybe the simplest way of understanding this is that if I look at at the late time profile of this h mu nu. If I take h mu nu and I go to late times, then if I look at the generating function of correlators of this field, it would be some objects. Let me call j ij, because now it only depends on the spatial indices, and it satisfies a constraint, a shortening constraint. It looks like this, j is 0. So this removes 1 degree of freedom, and that's essentially the reason. It's some bizarre thing about representations here of the de Sitter group that I don't know what to make of it, but I just point it out. We, as I mentioned, we don't know how to write an interaction theory of this particle, so it probably doesn't exist. But anyway, so that's the remark. So this, by the way, okay, now that you asked me, this persists at higher spin. If you go, for example, to spin 4, then there is the principal series. This principal series. Then there's the complementary series. So this looks like massive fields. These look like massless fields. So j equals 4, you would have 9 degrees of freedom here. Then at this point here, one of them decouples, you get 8. And then there's massless, m squared over h squared. There's some numbers that I don't remember. These are 8 degrees of freedom. These are 2, the standard, what you would expect from flat space when the m squared equals 0. And then there are some islands in between. This is a bit crazy. So there's a particular value of the mass that you have 6 degrees of freedom, particular value of the mass that you have 4, and then finally 2. Who ordered that? But they are bona fide representations of the de Sitter group. So this is forbidden. This is forbidden. This is forbidden. But these are good EREPs, and from here on you have a continuum. So these are called. This is, I think, Stanley Dazer and Andy Waldron called them partially massless fields. They're,
and this pattern holds in general dimensions as well, with a number of degrees of freedom.
I know the story in 4D. I don't know the story. It has been done, but I just don't know. I can't make the firm statement. Mentioned different than 4.
And there's nothing deep about the fact that the mass, when it's the same as the mass of the conformally coupled scalar, that you end up with this one loss of degree of freedom. There's nothing like.
For spin 2, I think it's a coincidence because it's a different value. Okay. Okay, so this will be my last point about phenomenology, and then we're going to put our formal theorist hat for the rest of the talk. But I want to write a formula that teaches us how to do spectroscopy. So if I take the 3-point function, zeta 1, zeta 2, zeta 3, of 3 scalar perturbations, and then I go to this squeezed configuration, I'm going to take 1, 2, and 3. So K1 is much less than K2, which is order K3. Then there is a nice way of, there will be some coefficient up front that sets the size of the 3-point function. And, cube. And so this is how you do spectroscopy. So delta is essentially the mass of the particle in Hubble units. It follows the, if you know ADS CFT, this will ring a bell. Follows the standard mass formula of ADS CFT, but with an important flipped sign, minus m squared over h squared, such a way that when the mass is bigger than Hubble, certain amount bigger than Hubble, the solutions to this quadratic equation become complex conjugates. So at which point you're going to have a complex exponent, something that doesn't happen in the context of ADS. So delta plus minus the two solutions are going to be 3/2 plus or minus I mu once m over h is bigger than 3/2. In which case then you can't just keep, usually we just keep the the slowest fall off if the mass is light, right? So it's called the growing mode in cosmology, the mode that redshifts the slowest. So as the particle propagates, it's redshifting away. That's why this is decaying. Okay, so the lighter the particle, the more efficient it is at communicating correlations in long distances. Once the particle is heavy, then you're going to have oscillations, and the suppression will appear in the coefficients. So as the particle gets very heavy, you start having Boltzmann suppression. Okay, so the coefficient will have an exponential decay with the mass. Okay, so once the mass is heavy, actually this is not quite the best parameterization, then you should write that formula. So this is for light masses. And for heavy masses, it will look something like this. It will look like, do you see with this stuff here, if I write here? Yeah, okay. So you're going to get something that looks like this. C, there's going to be some e to the minus pi mu. So this is Boltzmann suppression, essentially. Times, there's going to be some envelope that goes like 3/2. This 3 is just because of the usual decay of a massive particle, like a redshifts away like matter, a cubed. Times, and there's going to be a feature, cosine mu log, but it's logarithmic, it changes very slowly. But there's some oscillatory feature, with some phase that is actually predicted by unitarity, because it's related to the competition between the two different modes with plus and minus sign. Okay, it's related to spontaneous particle production and the pair production rate. So this phase is predicted by unitarity. So a couple of cool remarks about this formula. One is that this massive particle really traces the background geometry. You see, in inflation, we'd like to say that there is some expanding universe that sets up the perturbations, but almost scaling variance is very crude. Well, if you have a new particle, then as you dial this 3-point function, you really see the 2-point function. The particle is like really propagating through this background geometry. As it propagates, it picks up a phase. So this is essentially a phase that's coming from time evolutions, e to the imt, from propagating from time t1 to time t2. That's why the signal is going up and down. And the overall phase of the signal is dictated by essentially the facts that there is a rate of pair production, of how much you have of positive frequency versus negative frequency as a function of the mass. So this is a kind of a beautiful formula, and you really see time evolution just by dialing some distances in the sky. So you have the triangle. As I squeeze the triangle, the signal is going to go up and down, because this particle is propagating a certain number of Hubble volumes and creating either constructive or destructive interference as it travels before it decays into the other pair. Okay? So this is time evolution without time, just by dialing these distances in the sky. So this is going to be some sort of theme when we try to bootstrap these shapes from first principles. Last comment is that, so this is how you do particle spectroscopy. So this would be, there was discussions about Paul mass and Lagrange. So this is sort of like Paul mass. It's not really, I mean, for a scalar, this is the mass that appears in the Lagrangian, but the mass that appears in the Lagrangian for a spinning field is not very closely related to the exponent that appears here. For example, this exponential suppression only appears for principal series fields. All the fields in the complementary series, if they're light enough in Hubble units, they all look like massless fields from this point of view of Paul mass. It's just the decay rate that changes a little bit. And then,
but in this formula, 3/2 is a real part. So essentially, delta, you have a real part, right, which you wrote, and
yes,
imaginary part which gives you cosine, right?
That's right.
Right, but it is still like a complex power, right? It's not like, I mean, it's special.
No. If the particle is light, the delta is real.
Delta, your delta.
Yeah, so if m is less than 3/2 Hubble, then
But your delta plus is not.
that's so delta plus and delta minus are real, but we just keep the one that decays that's lower. There is also, of course, some other parts, but I'm just writing the leading contribution in the squeeze limits. So the leading fall off as I create this hierarchy. There are going to be corrections to the formula. You're absolutely right, and then they depend on delta plus. It's just that when the mass is big enough, the two deltas compete with each other, and you get the oscillations. They both have the same real part.
How does it work when I convert between wave function coefficients and the cosmological correlators?
I didn't say a word about wave function coefficient yet, so it will. So let's postpone that for. It's like going from the scattering amplitude to the cross section, right? There's some squaring and so on, but.
Yeah, that's why I'm getting confused about the phase.
No, I think that the phase and everything is there also in the wave function coefficient. But anyway, we can talk about it later. Okay, so I think I'm done with. No, I'm not done. I forgot to mention this. So this is how you measure mass, and this is how you measure spin. So if you take now this triangle, 1, 2, 3, and you dial this little angle here, if you look at these two guys as a polarimeter and you move them around, then the signal is going to go up and down depending on the spin. You couple to the longitudinal mode of the spinning particle, but then here the signal is going to go up and down because of the way of the derivative coupling between the scalars and the spinning particle. And you get, more or less from representation theory, you get some Legendre polynomial-like behavior. So the signal bobs up and down as a function of this angle. So this is how you do spectroscopy. It's very similar to particle physics. The sad news is that in particle physics, when you detect a new particle, a cross-section grows. You get a spike. Well, and then you go, you sit around the pole, and then you study the decay, you study the angular distribution. Here is about where the signal is weakest, that the mass signature is clearest, because you're just giving enough Hubble volumes for the particle to propagate. So the signal is strongest here, where you have self-interactions, but it's rather boring, featureless. And then as it decays, depending on the way that it decays, that's how you're going to detect particles. So because the experiment is run at a single energy scale, you can't really crank up the energy and put things on shelf. Right? It's already run for you. The only thing you can do is probe different geometries. Just the way it is. High energy, but low luminosity, so you do what you can. So, okay, so I think that's it when it comes to phenomenology. I could say things about strongly coupled sectors, about loops and so on, but I think it gets a bit too much into the weeds. So you could imagine sticking other types of things here. For example, computing this at one loop, for example, for a bubble diagram, it's getting understood as we speak. Even a triangle diagram, if you have some fermion loop and so on, is still sort of an open problem. So very simple things. They're flat space analog. We still don't understand how to do in cosmology. You could imagine, what if I have some strongly coupled sector, something like a QCD-like sector, and then you couple it to some operator that has an interesting two-point function, then how do you go about it? So, for example, one thing that I'm doing for just to get your feet wet to investigate this, to couple to what George I call unparticles, right? So you just couple to have some CFT in 4 dimensions with some interesting anomalous dimensions, and then you weakly couple it to the inflaton. This was studied actually partly by Matias Adariaga, who's around, but they only understood this part, the particle detection piece, the decay. But now with these methods that I'm going to explain to you, we can bootstrap the whole shape and so on. But it's interesting, if I have some QCD-like sector with lots of resonances around the Hubble scale, then you would have some big interference of all of these various oscillatory signals, and I'm curious to understand if there's a new shape. Because I think I mentioned this in the first part of the talk, but let me re-emphasize. If you have a well-motivated shape from theory, you can search it now, because it's not that we measure the bispectrum of the data. We try to fit the data with a well-motivated bispectrum. And for example, you can go on a fishing expedition and try zillions of shapes, and you will find 3.5, 4 sigma, but okay, it's all look elsewhere. So it would be nice to have maybe to motivate also why I would say that you can UV complete the sigma model with things that are weakly or strongly coupled. Maybe there are other possibilities that we haven't mapped out yet. Okay, so I'm going to leave my phenomenologist hat in here. I'm going to put the theorist one. And now let's talk about bootstrapping. And by bootstrapping, I mean something really primitive. Just trying to calculate these correlators from basic principles, just from their symmetries and from their singularity structure. Not something as sophisticated as what's done for the S matrix or for CFTs. Just trying to use general principles to understand the answer instead of doing perturbation theory, standard time evolution. So let's try to understand how to bootstrap the correlators. So I'm going to reset, okay? So forget about inflation, phenomenology, and so on. And I'm going to start with a very simple thing, the Hartle-Hawking wave function in flat space with no gravity for a massless field. Okay? Hartle-Hawking, I really just mean the Schrödinger wave function. We're going to do QFT, but using the Schrödinger wave function. Okay, so for a massless field. And we're going to get our feet wet to learn something about the structure. We know that flat space scattering amplitudes, for example, at 3 level, they have a very simple singularity structure, only poles. We know where the poles should be when you send some Mandelstam invariants to, for example, in a massless theory, send some Mandelstams to 0. So we want to understand what's the analog for the wave function. So the wave function, Einstein was asking about the wave function. It's a primitive object from which you get this correlator using Born's rule, like in standard quantum mechanics. So you take the wave function. What is it? What is the question that is answering? It's trying to compute the overlap. So it depends on some data, say some field profile, this scalar field profile as a function of x at some time eta star. And it's just giving me the probability amplitude that at time eta star I have the scalar field with some C number profile phi of x. And because Hartle-Hawking, it's the vacuum wave functional. So what's the probability that in the vacuum, if I just cut at time eta star, what's the probability that I'm going to measure some profile for a scalar field phi of x? Okay? So that's you can do this, we're going to do this essentially by saddle point approximation. And from here you get correlators. So to get correlators, this type of correlation functions that we've been discussing, then you just use Born's rule. So for example, phi of x, phi of y would just be, you integrate over all C number phi's, phi of x, phi of y, psi squared, properly normalized, right? In perturbation theory gives you, this is going to be almost Gaussian, and there's a simple map between these objects and the coefficients of the almost Gaussian wave function. We know from observations that we expect this to be almost Gaussian wave function. So let me start with the dumbest example, which is just the free field. So here, you take 2 points, 1, 2. There's only one thing to compute, which is the spread of the Gaussian wave function. So psi is going to be the exponential. It's going to have form that looks like this. It's useful to go to momentum space because there is a spatial translational symmetry. So you go from x to some Fourier modes k, and you integrate. There's going to be some quadratic wave function coefficient that we call psi 2 times phi k, phi minus k. So for every partial wave of this spatial profile, you're going to have a certain wave function coefficient that I'm calling psi 2. By the way, the
Massless.
yeah, I'm doing massless. For flat space to go from massless to massive is very simple. I'll show you in a second. So you can do this computation, and you're gonna get. You can do you're just trying to solve. You can do by saddle point approximation. You compute the action when you have some boundary condition of the field to have some spatial profile phi, some wave number phi k. At this time eta star, and you want to select the vacuum, so you need to go a bit into imaginary time, and that selects, even though you're computing e to the is classical, the saddle is complex, so you end up with a wave function that is not just a pure phase, and this is the answer. It's not surprising. And to address David's question, if you were a massive field, it would just be a frequency with the usual formula. But I'm going to talk about massless fields, so let me just keep it with K here. By the way, for the rest of the talk, this is notation, but it's very useful. K is the absolute value of K. And in flat space, of course, it's the energy for a massless particle. And in cosmology, by abuse of notation, I'm going to keep calling it energy, even if there is no conservation of energy. As you see, it's very useful for intuition. Okay.
Just to regards my question, because you're taking mod psi squared, is the phase actually coming from the fact that the field profiles are now complex when you have the principal series fields? When you do the Born rule?
No, I think that the wave function coefficient, the real part, we already have all of this stuff here. It's not from the mod squaring part. Yeah. You see, in the end, all of this is just measuring the 2-point function of the. So it's all encoded in the 2-point function of the messenger particle. So you should really think of these external curvature perturbations as probes. And then as you dial the geometry, all you do is you're measuring the 2-point function of the thing I just deleted here from the board. Okay, but it's essentially a translation of the 2-point function of the messenger field. The only thing is that you convert the times in which this is anchored to some momentum scales because of this story that particle production is most efficient when the physical wavelength of the mode is of the order of the Hubble radius during inflation. That's essentially the whole complication. Okay, so this is Gaussian, and then you use Born rule, and you get that the 2-point function is 1 over 2k. So it's just the inverse of the coefficient of the wave function. And for example, there's already something a little bit cute if you do the massless scalar in ds. So this is the massless. This is a side remark. I'm going to keep in flat space for the next 15 minutes, but I just can't resist. Let me just little parenthesis. The massless scalar in ds, if you compute the wave function, the Gaussian wave function, it looks like this. It has an interesting phase. Strictly speaking, yeah. So as I send the now I'm in conformal time. So Les Dixon was asking me, am I in conformal or in physical time? Now I'm in conformal time. Let me write the metric in a second. So now it has a phase. So here it was purely real. But if you do the same saddle point type of computation, there's a phase, and this phase is very big. It's some WKB phase, which is what this Harton-Hawking saddle points really know about. And moreover, it's local in position space. So there's a whole thing called holographic renormalization that people do in the case of ADS to absorb this into a local counter term. But now in the sitter, this is the imaginary part. So it's not exactly clear if you try to do holography in the sitter space how to think about this. You need to think about something like imaginary counter terms and so on. In any case, it doesn't matter for the observable, because when you take mod squared, then this is what gives the almost scaling variance, the 1 over k cubed we were talking about in the first lecture. So this is just a side remark. And of course I need to write, so the metric for the sitter space in conformal coordinates is given by this. So that you're probably used to seeing this in this way in FRW. And there's a simple formula to go to conformal time that then time going to infinity, cosmic time going to plus infinity corresponds to eta going to 0. So as you send eta to 0, this phase becomes bigger and bigger, more and more oscillatory. But somehow the expectation value of the massless scalar only cares about this, this piece here. Okay, so let's go, so the end of parentheses. Let's go back to flat space, and we're going to start to learn something. Let's now compute a 3-point function in phi cubed. Just the simplest thing you could imagine. Now you have 3 points, 1, 2, and 3. And you want to integrate over this vertex. So you need a propagator for that. And you want the propagator to set up some partial wave with amplitude phi k1. So now there's going to be a Gaussian part that I'm skipping, plus integral psi 3, some wave function coefficient that depends on partial waves of wave number k1, k2, and k3, okay? And then I can again use Born's rule, and because this is small in perturbation theory, I just knock it down by expanding the exponents, and I can relate it to the 3-point expectation value. So to compute this psi 3, I need some propagator that sets up some partial wave with amplitude phi k1 at this surface eta star. And that's very simple because it's a massless field. So the propagator is called the bulk to boundary propagator. It's just given by this. It's just given e to the I. I'm just normalizing so that it has unit amplitude. So for momentum k, of course it depends on the momentum k, and it sets some unit amplitude at eta equals eta star. Okay, so then I just integrate these 3 bulk to boundary propagators. And so far, you look awfully similar to what you would do in flat space to compute an amplitude, but now comes a mild difference. So the wave function coefficient would be an integral over this time, eta, of these k1, k2, k3, which is integral d eta e to the I. I can even shift eta star to 0, not to keep track of this. Now I integrate from minus infinity to 0, e to the I k1 plus k2 plus k3 eta. Okay? There's going to be some coupling constant. If this was g phi cubed, there'll be some g here. And this would give me energy conservation if I were doing it in flat space and integrate from minus to plus infinity. It would give me the standard flat space energy conserving delta functions. These are just the sums of energies. Now, because I integrate from minus infinity to 0, there is a pole. Okay? So that's the answer. So that, okay, maybe there's an I. Okay. Yes, well, that's true. But in the physical sheet, you never see it because these guys are always positive. But if you want to understand, actually, this was a point that took time for people to understand. If you want to understand how to do unitarity cuts properly and so on, there is an I epsilon here because eventually when we want to analytically continue these and make some of these K's negative. So it's an important remark. But in the physical sheets, this is the answer. Okay. Now, so that's already a novelty compared to flat space scattering amplitudes in that cosmological correlators, even for contact diagrams, have singularities. But they have only one singularity. You can prove that any contact cosmological correlator, if it comes from self-interactions like this, only singular as the sum over the ki's goes to 0. Okay? And that's the only singularity that is allowed. And, well, what happens when you send, of course, these are all positive numbers as the absolute values of the momenta, but if you think of k as square root of k squared, then you can imagine going to the second sheet, making one of these negative, and then trying to send the sum to 0. And then one needs to be careful with I epsilon, like David was saying. But nonetheless, if you do that, then what happens is that the amplitude the wave function will blow up, but the coefficient up front will be Lorentz invariant. You will be Lorentz invariant, and you will be the scattering amplitude for the exact same diagram. Okay? So the claim is that psi, any wave function coefficient, as I send this limit, sum over ki to 0, it will blow up. In flat space, it always blows up as a pole. In de Sitter, the blow up can be more sophisticated, times the flat space scattering amplitude. This is sort of a general statement. So it's actually a good guiding principle because it's a sanity check. It connects to the physics of scattering amplitudes and somehow shows that this wave function is a bit of a generalization of a scattering amplitude. Okay, it has support away also from the energy conserving delta function. Okay, so this holds for any diagram actually. That any diagram will always have this what we call total energy singularity, and when it blows up, and when it blows up, you get as the residue the flat space scattering amplitude. Well, the reason is very simple. When you send the sum of k's to 0, then the integral is getting peaked at earlier and earlier times, so then you really forget about the boundary. Okay, so you're just really doing the computation in flat space in the end without any boundary. So that's the cool thing is that it remains true even when you switch on a cosmology. Because if you have something like de Sitter space, if you somehow probe kinematics that pushes the integral to be peaked at very early times, if you go backwards in time, you blue shift the modes so much that they don't know they're in curved space. So you again reproduce the flat space scattering amplitude. So this will be very useful to bootstrap these. Okay, so we learned something. So in flat space, what would be determined by Mandelstam invariants, just polynomials of Mandelstams, is slightly more sophisticated. in cosmology because you're allowed to have poles in the total energy. So let's study now next example, which is an exchange diagram. And then after this, we're ready to go back to cosmology. Okay, so say you now want to compute, again, this phi cube theory, massless, but now you want to compute this diagram here, okay? So now you need a propagator from this point to this point, and this is called the bulk-to-bulk propagator, and let me write it to you, and I'll make a comment. So eta 1. Of course, you need to stick in propagator from eta 1 to phi 1, eta 1 to phi 2, eta 2 to phi 3, eta 2 to phi 4. Again, I'm interested in a wave function that has a Gaussian part, but now we'll have a non-Gaussian piece that has a psi 4, phi 1, phi 2, phi 3, phi 4. Okay? So I will need, so psi 4 is going to have integral over d eta 1, d eta 2. I have to integrate over 2 times, minus infinity to 0. And I'm going to have propagator 1 and 2 starting from eta 1. This bulk-to-bulk propagator, eta 1, eta 2, with some momentum k, the exchange momentum, times k3, eta 2, k4, eta 2. Okay? So this, I think, is pretty standard. It's just the propagators that take you from here to here. And now you have this guy here. And it would be almost like you would expect from canonical quantization. Of course, we have much fancier ways of doing that in flat space because you have full-blown relativistic invariance. But now we broke time translation symmetry, so we need to work in this hybrid space-time approach, and we're going to be able to integrate in cosmology by doing that later. So it looks something like this: eta 1 minus eta 2. Then there's the other time ordering. And now there's a novelty because you want this propagator. You already set up the boundary conditions with these guys here. So you already switched on some background wave with partial wave phi k1, phi k2, phi k3, phi k4. So this propagator better do nothing to you when I approach this. And if I set eta star to 0, so it needs to satisfy a boundary condition that it vanishes. As I said, either eta 1 or eta 2 to 0, which makes it not quite the same as the Feynman propagator. So you need an extra term that looks something like this. It's going to break time translation symmetry. It's a plus, it's not a typo, okay? It's just ensuring that the propagator vanishes when I drag either this point or this point to the boundary. And then you can do the computation, okay? It's very simple, it's just product of exponentials, and the answer is kind of neat. So there are 3 terms, and they add up to something nice, something nicer than each individual term. And they also have an interesting geometrical interpretation. Then I go on a tangent for just a minute, and then we go back to real world. So the answer looks like this. So of course there's coupling constant here, G and G. Psi 4 is given by this formula, G squared, K1 plus K2. This is our brand new friend, total energy singularity. But now there are 2 new things. K is this guy. This is always confusing, so let me make sure. K1 is mod K1, K2 is mod K2, and K is mod of K1 plus K2. Okay, so this is not the same thing twice. K3 plus K4 plus K. Okay, so this is the answer. So now there are three singularities. Let's go back to the diagram. One, two, three, four. There's a singularity when you send the total energy to zero. The total energy of the process, when you send it to zero, then what happens? This becomes minus K1 minus K2 plus K, and then this object combines into a friend. It becomes 1 over minus K1 plus K2 squared plus K squared. But what is this? It's just P1 mu dot P2 mu, just the Mandelstam. 1 over the flat space Mandelstam. When I send E total to 0, 1 over K1, 2, 3, 4. Okay? So it gets our usual Mandelstam. So that's one singularity, but now there are two new ones which are related to, so what was the physics? The physics is I'm dragging both times to so early, they're so blue shifted, I'm doing the flat space scattering amplitude. But now I got some sort of centaur, some bizarre objects, which I can do is the following. I can now take this to 0. These are the energies that flow into this vertex. So what I do is I take this guy to the past, and I keep this one fixed. So what happens is I think, as far as I can tell, is the closest one can do to factorization in cosmology. In amplitudes, you factorize by putting a particle on the mass shell. Here we can't. What we can do is we can drag the interaction vertices apart in time. And that's essentially what this limit does. So in this limit, I get 1 over K1 plus K2 plus K times G, which is the flat space amplitude for 3 particles, times something that, let me call psi 3 tilde, that is not quite the 3-point wave function coefficient, because when I drag this guy to the past, you see this leg becomes sort of incoming instead of outgoing. So I need to fiddle a little bit with this wave function coefficient. You can attach words to it. Maybe let me not confuse you with the words. But if you want to know what this is, psi 3 tilde is really the 3 particle wave function, which we just computed. It's just K1 plus K2 plus K3. But you take particles 3 and 4, they are never touched, but you're allowed to flip the energy of the intermediate particle. That would be fine if you just draw the diagram, because you could think of this guy as incoming, but there is a second term, which is the standard 3-point wave function plus K. You can prove this by the diagrammatics. I can maybe give you some intuitive reason why. This usually comes from some Schwinger-Keldysh approach. You prepare the vacuum, you time evolve, but then you need to prepare the vacuum from the other side and time evolve to compute this expectation value. You can think of this lag as being incoming from one side or incoming from the other side. Okay, these are words, but this is the answer. Okay? The point is that then in this limit, it's really like a factorization limit, because you can write the 4-point wave function coefficient in terms of lower point data, right? This is the 3-point scattering amplitude and the 3-point wave function coefficient. So this is a general result. In flat space, all singularities at 3 level, they are, first of all, in the physical sheet, the wave function coefficient for the vacuum never blows up. This is the first result. So the idea of putting things on shell and so on, at least for this type of kinematics, is impossible, because it's vacuum wave functional. You're just taking a vacuum diagram, a bubble diagram, and slicing it by taking a time in which to observe the process. So you never see things on shell. The only way to go sort of on shell is to analytically continue and take some of these partial energies to 0. Then there's, let me go into La La Land for a second, because it's very beautiful. So one way to think about this answer here, if you look at kinematic space, so this is another observation, okay? We go to kinematic space, 1, 2, 3, 4. This is an exchange diagram, so you can imagine triangulating kinematic space like this, because this is the exchange momentum. And you can think of this exchange diagram as living in the dual space. Okay? And the answer is essentially the product of all perimeters of this polygonation. If you look here, this perimeter is the total energy. This perimeter is this guy here, and the perimeter is this guy here. Okay, so this is the product. This is also G squared over the product of all the perimeters of a polygonation. So there's a nice story to Nima with Paulo Benincasa and Postnikov, where they first of all they proved that this is sort of a general statement for this theory. You can write the wave function coefficient as sort of a product over all polygonations. Okay, but then if for bigger polygons, then there are multiple ways of triangulating, so you get multiple terms. But for each term, you just take the product of all perimeters. And moreover, they found one of these positive geometries, something called the cosmological polytope, whose sort of volume, not really the volume, but doesn't matter, something called a canonical form, kind of knows about this answer. Okay, so that's kind of neat. And that's a side remark. The other side remark is that you can see this. For a long time, we thought of this as kind of a really crude toy model of cosmology, but you should really see this as building a Christmas tree. Okay, this is the skeleton, and now you need to start attaching the bells and the whistles. And so let me give you an example. So if you take this wave function psi, and it depends on these external energies and the internal energies, and let me just change notation for a second, okay? Just indulge me, okay? It's not really the point of the talk, but I can't resist. So you take these collective variables, K1 plus K2, and let me call them X1. You see, it doesn't depend on K1 and K2 individually. They always appear in the sum. So I don't want to keep them both around. So this is a wave function that really depends only on x1, x2, and k, the exchange momentum. So now there's different dressings that you can do to this function that will give you cosmological stuff. So this was all in flat space, if you will. But now I show you two examples. One is in print and the other is not. It should appear soon. The first example is if I take this wave function and I shift by little Feynman parameters. And now I integrate this against a measure. So now I get some object, some new wave function that depends on this parameter epsilon. This is the first example. Okay, so it depends on the parameter epsilon. So I claim that if you check, I had a rational function, and now I integrate against this measure. This Feynman parameter integral runs from 0 to infinity. Now it starts to look like a loop integral. Actually, you can, I learned all sorts of things about Laporte algorithm and twisted cohomology, many beautiful things to understand these integrals. And if you change epsilon, so this, you see, if you look at it, it's just a bunch of rational functions integrated against a measure like this. It looks like GMRAG, right? Some propagators and a loop integral. But here, what you change as you change epsilon is you change the cosmology. So I claim that this parameterizes the same diagram, but now with a scale factor. A of eta, that's given by this formula, 1 plus epsilon. So if I change epsilon, I change the cosmology. Any power law cosmology can be achieved by changing epsilon. And this is not totally arbitrary, but it includes all the cool cosmologies, like epsilon equals 0 is the Sitter space. We really called epsilon because if it's small, it's sort of slow roll inflation. But epsilon equals -1 is flat space, and it's a non-trivial result. This is logarithmically divergent, but if you stick in epsilon equals -1 and regulate, the integral spits out the same rational function, which is a prediction of this map, and it's true. Epsilon equals -2 is, I think, a radiation-dominated universe, -3 matter-dominated. So all the cool cosmologies are parameterized by this. So that's one deformation, and
Does it hold the positive epsilon?
I think it holds for any, whatever epsilon you put, it will correspond to an epsilon here. Whether the cosmology you end up with is healthy or not, I think is a separate question. Right? Let me just give you another deformation. I think that we have not mapped all possible. Just think of this as the Christmas tree, just the skeleton, and this is a way of putting Christmas balls on top of it. And I should.
Works for any graph?
It works for any graph. So if I take now, for example, yeah, you need more Feynman parameters, of course, but then it works for any graph. So.
And this x1, x2 is basically shifting time.
Yeah, it sort of implements the fact that you should be integrating with a different weight time evolution here. So the number of integrals changes depending on the graph. So if I take a graph like this one, for example, 5 points, then there is some flat wave function that is rational. It's going to depend on, let me call this coordinate x1, this momentum x2. I know it's cognitive dissonant, but okay. x1, x2, and x3. This is y and y prime. And yeah, this will be the cosmological wave function. Okay, so it always works. It's, yeah. Anyway, this solves a beautiful system of differential equations, and we can even kind of predict all the differential equations from some graphical rules. And there's a whole, if you gave me 3 more hours, I would tell you everything you would wanted to know and didn't know you wanted to know about this wave function. But let me just tell you one more example that is not in print, because of course the skeptic would say, okay, this is one way of attaching bells and whistles, but I think there are more, and we haven't fully mapped. So another thing you can do is take the flat space wave function. So here I was just shifting these external energies. If I keep them untouched, and I shift now the exchange, and I integrate against a kernel that looks like this, t squared minus 1 to the delta, from 1 to infinity. This is some psi delta wave function. And what is the physical interpretation of this? The physical interpretation is that now I exchange, well, in this diagram here, I exchange an particle. I exchange a CFT primary of anomalous dimension delta. Okay, so there's another way of attaching bell and whistle. There are other ways, but okay, maybe I stop here.
Or it's just for massless particles?
This is for these two deformations are for massless particles. There's yet another deformation which you can add mass to it at the cost of more of these bells and whistles. Yeah. So, for example, if you now stick to the Sitter space, there's a way of adding sort of these T-type of parameters, and engineer, if you wish, the conformal dimension of the growing, the decaying mode, and engineer a massive particle in the Sitter. And this is a brand new result. People just noticing it.
Well, so there's a way of doing this for flat space, adding a mass by this kind of thing?
For flat space and adding a mass, then I think it's if you always think of this as omegas and write omega is root k squared plus m squared, then that's it. But the mass in the Sitter is very complicated, and the only way I know how to do it starting from this point of view is to do this deformation. Yeah. But massive particles in FRW, then all hell breaks loose. I don't know what to do. Okay. So, sorry, let's go back to, but this is kind of beautiful, so I wanted to mention it. So now, what was the point of this excursion into these computations is to learn that we know we're doing the right thing if the correlator has singularities. So remember, we wanted to understand this density perturbation correlator when I exchange a massive particle, and I run out of red. So, we wanted to do this particle detector type of arrangement. And now let me do 4 points, just because the analogy with flat space amplitude is much cleaner here. Okay. Now I exchange a massive particle. So what is the point? I would like to claim that in de Sitter, the nature of the singularities will be different, but the singular points should be the same in kinematic space. Only, so it should be consistent with de Sitter kinematics, and singular only at these three guys. Okay? E total and E partial in the left and on the right. I'm just writing this S-channel diagram. Of course, then you have to sum over the permutations. Okay? So it should only have these three singularities. Let's try to see if it's possible. Well, I wouldn't be here if it wasn't possible, so it is possible. Let me show you. So what should the answer look like? So it should be something that around when all the momenta are of the same order, it should look like a self-interaction. It should just look like a self-interaction when K1 or K2. It should look like equilateral, non-Gaussian. Okay? And otherwise, I should measure the two-point function of the messenger when there's a hierarchy. You should know about the propagator of the messenger. Now, so the fact that I'm in de Sitter now is going to allow me to do many cool things. Thing number one is if I do it for scalar exchange, I don't need to do spinning exchange. I can just put bells and whistles on top of the answer and get the spin exchange answer. That's thanks to the representation theory of the de Sitter group. So that's very useful. Uses something called weight shifting operators. You can even try to use this technology to get gravitons, but gravitons are a separate, very beautiful, separate story. So let me keep to external scalars for now. So we're going to do a scalar exchange of generic mass. And we want to first understand the kinematics, and then we're going to understand the dynamics. So first of all, we would like to classify self-interactions. At 4 points, there are many ways of a scalar field to self-interact, all possible types of operators that can appear in the EFT. So let's start with the dumbest one, which is lambda phi to the 4th. So, one more thing. I'm going to study conformally coupled scalars. M squared equals 2h squared, which would correspond to delta equals 1 and 2, the decay rates. So it's not really the physical thing. We want the massless scalar, which doesn't decay, delta equals 0. But because it's integer spaced from the physical thing, which is m squared equals 0, there's a way of, again, putting bells and whistles on top of this to get this. It's not hard to believe because the propagator for this guy is essentially the flat space propagator. It looks like this. While the propagator for this guy looks almost the same. 1 minus. So So you could imagine that if you massage this guy enough, you're going to get this guy. By the way, it looks simple for these particular values of the mass, but for any other mass, the propagator is a Hankel function. Okay, it's a Bessel function. It's complicated. These are the only places where we have safe anchoring. So we're going to use conformally coupled scalars. So what does kinematics give us? So kinematics. Well, there was a discussion after Steve Sharp's talk, so let's just count. So kinematic space has 12 pieces of data, right? 3 momenta for every particle, but the Sitter space is maximally symmetric. There are 10 isometries, so it should really be a 2-dimensional kinematic space, just like scattering amplitudes depend on S and T Mandelstam's. Same story here. And we're going to call them U and V because of the analogy with CFT, but they're not really conformal cross ratios, and we're not going to be able to fully diagonalize kinematics. So we'll pay some price, but as I'll try to convince you, we're still going to get something good going. Okay. So the wave function coefficient depends on these 12 pieces of data, K1 to K4. But thanks to, I'm going to diagonalize 9 out of the 10 isometries. Then the 10th one, okay, I fail. But I know what the consequence is. So the 9 isometries will give me this. So 3 of them just give me momentum conservation. 3 momentum conservation. That's good. Then scaling symmetry. Remember, the de Sitter metric looks like this. So it has an obvious rescaling of the coordinate symmetry, which doesn't exist in flat space if you rescale. That's why it's easy to get power law correlators in de Sitter. So the scaling weight of these massive particles is such that you get 1 over Ks here. Now I again change notation. Sorry, this is Ks because this is the S channel momentum. And it turns out that to diagonalize almost all the isometries but one, you should write a function of these 2 variables, Ks over K1 plus K2, and Ks over K3 plus K4. And we call this U and V. It's our poor man's version of conformal cross ratios. They're not, if they were conformal cross ratios, there would be no job left to do. But they're the closest we could get using momentum space. Okay, then there's one symmetry, one boost symmetry of the Sitter space that we didn't manage to diagonalize, but it implies an interesting differential equation, so let me write that for you. So now I'm going to just talk about this function here. It's a function of these dimensionless quantities, a function of U and V. And anything compatible with the Sitter kinematics must solve this equation. Delta U equals delta V, where this delta is a hypergeometric operator. Looks like this, U squared 1 minus U squared d2U minus U cubed du. So it has singularities at 3 different kinematic locations. U equals 0 plus or minus 1. Okay? So we'll get back to these singular points later. So, very good. Let's just, this was all kinematics. Let's do a dynamical example to see if this all makes sense. We start with the simplest thing, as usual. Just take lambda phi to the 4. These are conformally coupled scalar with a conformal interaction. So you'd say, well, it's the same as doing it in flat space, but for this boundary. We only do half of the time integration. Otherwise, it would just be lambda times a delta function. But just like we discussed in flat space, here the answer is just going to be 1 over the total energy, K1 plus K2. Okay? Yeah?
Are these deltas conformal Casimirs?
this delta, it is related, but not quite the conformal Casimir. Yeah, it is related to the conformal Casimir. By the way, it's good that you asked me the question, because Faye has studied the analog of this function in embedding space. If you want to do, so say you're a staunch defender of kinematics, and you're like, I want to diagonalize all the kinematics from the get-go, and you can do that by going to embedding space, because the de Sitter group is SO4,1, which Dirac pointed out already. It was reinvented millions of times, maybe most recently by Weinberg in 2010. But Dirac already noticed that this is just the Lorentz group in higher dimensions. So you should just think of Lorentz invariants in a bigger geometry and pull them back. And you get immediately conformal invariants. Okay, this is called embedding space formalism. So you can try to write everything that is consistent with this conformal invariance from the get-go. And if you try to do that for this example, just 4 conformally coupled scalars with a lambda phi to the 4 self-interaction, the objects you end up with in embedding space is kind of complicated, which is very frustrating. It's this polylog, this Lie-2 function that appears in 100 different places in physics. It's the box, massless box integral. Anyway, it appears all over the place. So, well, in momentum space, it's the dumbest thing you could write is just a rational function, 1 over k1 plus k2 plus k3 plus k4. Okay? Which is consistent with our rule of the game. It has only a singularity here. When you zoom in, it gives the flat space amplitude, which is lambda. Very good. So now let's see, does it conform with this? Then the answer is yes. So you can write it as lambda over ks times uv over u plus v. So this would be our f. And if you're very fast in Mathematica, you can punch it in right now, and you'll see that it solves this equation, delta u minus delta v equals 0. And now, well, then you automatically generate all solutions. Well, you're going to generate an infinite number of solutions to this constraint by just kicking it with delta u. So if I take delta u f, it's a second order operator. So I'm going to get u plus v cubed. It's, of course, going to still satisfy this, because delta u times delta u f is this, solves delta v delta u f. So delta u f is an acceptable solution of the kinematic constraint. It only has a singularity when the sum of energies goes to 0. But now it produces a numerator. And that's how de Sitter gets you Mandelstams, because Mandelstams come with energies, right? So you compensate with that by getting higher powers of energy downstairs. So you're going to get something that looks like 1 over k1, 2, 3, 4 cubed times s flat when you send the k to 0, k total to 0. It's very beautiful. You can check. This takes 3 minutes. So now if you keep delta u squared, delta u cubed, so it's easy to understand. You're going to get k total to odd powers times s flat to 1, 2, 3, and so on, the flat space limits. But you generate some complicated numerators, and you bootstrapped all, at least for this massive exchange, when you integrate out a massive field, you bootstrap all possible contact interactions, all the analogs of D functions. Very good. This is a hint of how to do the exchange. Why? Because now you should think of delta U on the support of these solutions of the kinematic constraints a bit like the Mandelstam S. So then we just go back to flat space, right? Flat space, if I take a scattering amplitude, then the solution is just S minus M, right? So that's the flat space scattering amplitude. And then you can just write the dumbest equation, which is this, S minus M squared M. So like, well, but I just learned that multiplying by delta U is a bit like pulling a Mandelstam. And this is the contact term from lambda phi to the 4. So I'm led to something that looks like the mass. And if you work a little bit harder, you'll see that this is the right thing. That's it. So this is the differential equation that the exchange solutions should solve. Let's check. It has the total energy singularity. Good, it should. Now this guy here has singularities at 3 locations at u equals 0, 1, and minus 1. But it's a differential equation, so I can at least kill some of them. At u equals 1, it's what? It's Ks equals K1 plus K2, and which is essentially just some collinear limit, 1. And nothing should happen here. It's not special at all. It's just some collinear kinematics. You're the vacuum wave functional. So here, you should forbid this to have a singularity. So set singular term to 0. This is a boundary condition to solve the differential equation. Okay, that's essentially selects the vacuum that you do in the vacuum wave functional. And now you go to u equals minus 1, and that's just Ks plus K1 plus K2 equals 0. But that's our friend from 10 minutes ago, is the factorization. So then it should be singular, and the singularity should be controlled by the product of the 3-point scattering amplitude times the 3-point correlator in de Sitter space. And in de Sitter space, 3-point functions, just like in flat space, are pinned by kinematics. Just de Sitter symmetry gives you a unique answer. So then you know how to normalize. Normalize by factorization. What happens at u equals 0? This is something that you don't really see in flat space, but it's a feature, it's not a bug. So the solution will go like u to the delta. Is particle production. It's inevitable. Now you're ready. So the amount of particle production is inevitable once you fix that you should not have this funny singularity in the collinear limits, and once you normalize it using the 3-point function. So you open up a cut as u goes to 0, and that's the funny thing. So now the cosmological correlator, even if you're guided by the existence of those singularities, it has a slightly more sophisticated analytic structure. If you work on the u plane at fixed v, then you open up a cut at u equals 0, and it stops at u equals minus 1, and you open up a cut, and at u equals minus v, there is a discontinuity that is related to the flat space amplitude. And here it goes like u to the delta, and the coefficient is related to the it goes to e to the minus pi mu. It's inevitable. And this doesn't have flat space analog. Notice that e to the minus pi m is non-analytic in Hubble, right? While all the contact-like interactions, say you wanted to rewrite this in terms of contact interactions, okay? You're like, well, okay, I'm a first-year undergrad. I'm just going to put this on the left-hand side in the denominator and call it a day. So this is the answer, which is a reasonable thing to do for 5 minutes. So let's see what you get out of it. So F naive is 1 over delta U. Now I'm going to expand in large mass, so let me just call this m tilde squared, the normalized mass, times uv over u plus v. So you can start 1 over m tilde squared uv over u plus v minus delta u over m tilde to the 4th, and so on. This would give you effective field theory, right? You're just generating the irrelevant operators. And remember that m goes like h, so m over h, so it's really h squared, here's h to the 4th. So it's analytic in h, But particle production is non-perturbative effect. It's go like e to the minus m over h. You're never going to see it in perturbation theory. So you really need to solve the differential equation to see this effect. You're never going to see it. In fact, the notion of integrating out a massive particle in de Sitter is slightly suspect, because this is a space-time with a constant energy density. So if you look at very long distances, anything can go on shell eventually. You can borrow enough energy from the space-time to pull giraffes on shell. Okay, so the notion of effective field theory and the renormalization group, I think we use it, but one should keep in mind that there is this peculiarity. Okay, so this is just a feature, and this is the analytic structure. Okay, so even the simplest correlator, just the three-level exchange of a massive particle, has some funny cut structure and so on. So we thought we had invented a new function, then we discovered that a French guy called Campé de Ferrier had already written this function like 100 plus years ago. But anyway, so maybe if we want to study a slightly more sophisticated correlator, then we'll discover a new function.
Plus one singularity point. Plus one is under different.
No, at plus one you forbid it. So there is a naive branch point here.
Right.
But you said there would be a logarithm here, u minus 1, but you force the coefficient to be 0 so that it's smooth here.
Particular solution.
Yeah. For the vacuum wave functional, that's what you. Then if you want to allow for a singularity here, then you need to. People say, oh, it's related to the wave functional for an excited state, for example, or something like that. This is also being studied.
Sorry, is that like not working in Bunch-Davis?
Yes, it is Bunch-Davis. By Bunch-Davis, I mean vacuum. Yeah. So here, Bunch-Davis would forbid this singularity.
What with the alpha vacuum?
It would allow you some admixture. So you would predict that you have something. This is the only way that I could imagine something like alpha vacuum making sense. You see, what? Okay, this is something. What is an alpha vacuum? You can quantize. In the end, these are a bunch of harmonic oscillators for each partial wave. And we usually quantize by saying that in front of A, I put e to the minus I omega t, because that minimizes the Hamiltonian, right? But here, there is no positive energy to minimize to begin with. So you are allowed, just by symmetry, to have an admixture of e to the minus I omega t and e to the plus I omega t. And these are called alpha vacua, because the relative coefficient, you call it alpha. But the problem is we don't really know how to do perturbation theory with this vacua, because perturbation theory relies on the I epsilon prescription, right? So when you go into the past, it's important that you have only one wave, so you can damp it as you go into the Euclidean time. When you have both, I don't know what to do. The best that I know of is to try to write this type of differential equations and then allow yourself to have this type of singularities. This would be my best take on what an alpha vacuum in an interaction theory would do. If you really wanted to do it by time evolution, I don't know, you would have to cook up some funny prescription to do it. And I don't think anyone has managed to do that. Am I out of time?
Yeah, it's 3:02.
Okay. I see, I got excited and I lost track. Okay, so let me say two more things and then I'll stop. Just to emphasize that this is time evolution without time, you just ratios of momenta. But just to make it sort of visceral, you can do something funny here. Of course, it solves delta u minus delta v equals 0. Okay, so there will be an analogous ODE in the v variable. So you should solve both. Okay, with the same source. But you traded mapping solutions to PDEs to a pair of ODEs that you can beat up with 19th century, 18th century mathematics. So that's what we did. But now, just for fun, okay? If you send u and v to 0, you can do the following rescaling game. You call f equals v f hat, and you call f hat e to the t over 2 F tilde, bear with me, U over V. I'm sending U and V to 0, but I'm keeping the ratio fixed, and I'm calling this e to the t. So this equation, this limit, let me call m over h squared minus 2 mu squared plus a quarter. It's just, mu is just a mass anyway. Just a, in this limit, F tilde solves this equation. Now it depends on a single variable. So this is what is this? It's just a harmonic oscillator that gets a kick. That's it. So the kick is from the expansion of the universe. And the oscillations are the standard oscillations of the harmonic oscillator. So when you plot the answer, this is around this U and V going to 0 limit. F of U and V. You're going to get some boring power law, like decay, around the equilateral limits, just parameterized by this, it matches this type of function here, around U order 1. And then it decays, but it decays with a hooray, okay? So instead of seeing a spike in the cross-section, you see that it decays and decays oscillating. So here you really see that it's time evolution, trading time evolution by ratios of momenta. I think I will stop here. You can add all sorts of bells and whistles to this, and something that is deep to my heart is understanding what happens when you put gravitational waves here, because Lance and other people taught us that the best way to think about massless particles is using the right kinematical variables, the spinor helicity variables. And it was my first problem in graduate school. Juan Maldacena told me, wouldn't it be nice to have spinor helicity variables for de Sitter space? And we tried and we failed. And now I'm happy to report that after 15 years, we found a solution to this problem. And I never thought it would work on twistors, but somehow the answer is twistors. If you just follow your nose and you try to repeat the Dirac strategy of SO1,4, embedding space and so on, but you try to enforce everything, you eventually led to something that when we looked up in the literature is called a twister. So then if you look at this, but twistors in flat space, they are applicable to theories of extra symmetry, conformal symmetry and so on. Here, because the Sitter group is the conformal group, they have a more primitive rolling life to parameterize correlators of gluons and gravitons. So this is something that I'm very excited about these days. But anyway, there are lots of things you can imagine doing, loops, strongly coupled sectors, and so on. So this is just to give you a taste of the joy of cosmological correlators. So I'll stop here.
Can I ask you a practical question? What are realistic prospects of future surveys? Where do you think we're going to get? Are we actually going to be able to discover any of this?
Well, I think if we measure FNL local, then I think there's a realistic chance that we can try to detect the power deviation. So you look at scale-dependent bias, right? Galaxy clustering, how exactly depends on scale. Probably, so the short answer is if this particle is very light, yes. These massive features, these beautiful features here, if you engineer, maybe, probably not. But I think if you have a very light particle, but spinning, the spin features are not, there are no kinematics. So maybe that one could imagine looking for. To get these massive features as beautiful as they are, I think it requires, I didn't say what happens when you break, strictly speaking, you could imagine breaking the Sitter symmetry quite brutally with speed of sound, for example. It tends to enhance non-Gaussianity, and it shifts the location of these oscillatory features. So you could imagine trying to push them a bit closer to where the signal peaks, but okay, that's model building. So maybe I'll mention, I like these two anecdotes from that Daniel Bauman taught me. So one is Peebles stopped working on the CMB because he thought it would take forever to measure the acoustic peaks. And Mukhanov said it would take 1,000 years to detect the tilt. So one was wrong by a factor of infinity, the other was wrong by a factor of 100. So as a theorist, I just say what people should look for, and then the observational people are very good at observing. So yeah, that's the anecdote.
Just to get back to the R parameter, do we know from general considerations that there's some lower bound?
Yeah, you could imagine you need to reheat the energies so that at least you can do BBN, and then H is ridiculously small. It's like you would have R 10 to the minus 60 or something like that.
Oh, I see. So it really could be very, very low.
It can be very, very low. I mean, the lower it gets, the harder it becomes to inflate. I mean, inflation becomes very sensitive to initial conditions, so the higher it is, the more robust it is to where exactly you start along the potential. But from the point of view of data, it can be ridiculously low. Yeah, 50 orders of magnitude away, 60. Maybe on.
Just as a phenomenologist, what do you think of non-inflationary Stein-Hardian?
I
kept the recording here if you'd like.
No, it's okay. It's okay. I think, well, okay, I never thought about it too deeply, but I have two comments. One, as far as I can tell, they can do the two-point function as well as inflation, but most models that I know, they are strongly coupled. The moment you start adding interactions, if you just, there's a nice power counting argument that actually Matthias wrote up 15 years ago, and they tend to be strongly coupled. So then you need to do some strong coupling dynamics, and it would be nice to get a prediction for the non-Gaussianities and so on.
Well, they have a prediction for R, right?
Yes, but the prediction is that it's undetectable. So
Well, that's a prediction.
Yes. That's true. That's true. Fair enough. But I would like to see, for example, there's an interesting new shape of primordial non-Gaussianity that arises from these models. I think that would be very interesting. Yeah, that's my comments. The other thing is that you could imagine trying to do these correlators for things that have this bouncing-like geometry, even at weak coupling, just to get a feel for where the singularities are, how they behave. Maybe even with weakly coupled computations, you can get an idea of what the correlators should look like. And I don't think this has been done.
What's another motivation for FRW correlators other than it's kind of close to slower or inflation?
The original motivation was that when I started talking about this, people were like, oh, but it only exists because of the Sitter symmetry, which is a fair point. And then we wanted to build a toy model where you could go away from the Sitter space. And I think the differential equations exist because you're essentially, the scale factor changes monotonically, so you're just trading a spatial scale with a moment in time. And that's what we showed. These differential equations do not follow just from symmetry considerations, Casimirs and things like that. So that's why we did it. But then after that, then we saw that there are other deformations and maybe they bring us closer to reality and so on. So, but that was the original motivation. Yeah.
Do you have a non-perturbative unitarity-like understanding of that cut?
In the Sitter space, if you go to different kinematical variables, then people have written something like a Chow and Lemon decomposition and the positivity of partial waves. But here, no, I don't know how it works beyond 3 level. Even at one loop, I don't know what the singularity structure is. For example, one thing that people do in ADS is go to this Melling space to make a dilatation symmetry manifest. And there what you get when you exchange a massive particle is an infinite series of poles. And my take on these cuts is that it's just squashing the infinitely many poles into a continuous cut in a finite range of kinematics. But that's all I can offer. Now the short answer is no, I don't understand it, non-perturbatively.
Is here, this differential equation applies for a massive scalar exchange, and I guess you also mentioned that if I want to consider a spinning particle exchange like graviton, you can apply.
Yeah, you essentially take this function and you apply some differential operator to it, and you get the spinning.
Do you know how do you systematically?
Yeah. We have a 150-page paper on how to do this. Bells, whistles, external particles, and so on. The moment that it gets kind of more deeper is when you put external gravitons here, because we know that the exchange diagram on its own can't make sense. But you think you're doing the right thing, and then you find that there's a very subtle breaking of conformal symmetry. The only way to fix it is to add other diagrams in a way consistent with the equivalence principle and so on. So we're discovering a la Veltman how to build these things, and meaning you just stitch together Feynman diagrams and you see that it's compatible with the symmetry constraints. But these twisters, I'm dreaming they will just force you to get the right answer from factorization, all the diagrams all conspiring together, just like we do in flat space. But we're not there yet.
So, for the sitter, is there a way of getting most of these by analytical continuation on each?
Yes, that's what Slate and Tarona did. It's slightly complicated because there are two ways of analytically continuing A. Is H goes to plus or minus IRADS, and you need to take the right admixture of both branches to get it right. It is possible, is the short answer, but it's not as trivial as just, yeah. And all of the computations in ADS are done in embedding space, while here, to connect to the intuition and scattering amplitudes, we go to momentum space. And I think we're discovering new things, like the simplest example is this D function, just lambda 5 to the 4. It's complicated in embedding space and as dumb as it gets in momentum space. So